Question 1 of the practice midterm is a method of images problem where we're given that a charge negative q is placed in the corner of two infinitely conducting planes. We can assume that the planes extend to infinity in both this direction and that direction, and they kind of form a right angle corner like this. Come together and we put a charge negative q a distance d over 2 above the horizontal plane and a distance d away from the vertical plane. So the method of images can be used to solve this problem, and it asks for us to draw the image charges that would be needed in order for this to be satisfied. So we know from section 3.2, I think, in the online notes, so see 3.2 online notes for more information, and the method of images in the textbook as well. And there's also some other Lightboard videos that kind of explain the method of images, but this is similar to a problem we did in class where we want to know which image charges we need in order to satisfy this. So we can first off think that the conductors each act as mirrors. So we have a positive charge q, an equal distance below the horizontal plane, so d over 2 away, in order for this configuration to work. So that connecting plane kind of acts as a mirror, and we see the positive charge below. Same thing over here. We have a positive q here, so sorry, this is for part A. We have a positive q here, a distance d away. So again, the vertical connecting plane acts kind of as a mirror. We see an equal and opposite charge flipped across the same distance away on that side of the plane, and also in the horizontal direction. And the final charge that we're missing, that we need to complete this charge distribution, there is a fourth and final positive q in this bottom, my left corner, this bottom corner over here, which is now a distance d, and d is 2d away from this charge, and distance d over 2, and d over 2 is distance d away from that positive charge. Sorry, this is a negative q, not a positive q, negative charge. So we end up with a negative charge, which is the actual physical charge placed in the corner of this conducting plane. The positive charge is an image charge reflected below, another positive charge reflected across this vertical plane, and then, correcting my mistake, it's a negative charge that's in the opposite corner here, a distance 2d from this positive charge, distance d from this positive charge, and it's, again, almost like the mirror image across this imaginary line here, including this negative charge on the bottom. So that's part A, is it wants us to draw this configuration. So we had some examples of that in class. You've also seen examples where this is not necessarily a 90-degree angle, and we have this shifted by some integer value, and what that means is that we're going to have a different sort of image charge distribution. So I would recommend brushing up on all of those. I find that this was, when I took the course, was the most challenging for me, and after a couple times through it, I was able to kind of learn and understand more so what's going on. So you can definitely learn what happens when you have different angles and stuff. You just make sure you study that from these notes online. And part B asks for what are the physical conditions that are required in order for us to guarantee have this charge configuration. So the ones that must be met are the conditions on these conducting planes and the electric field in the space around it. So what must happen at the planes, and what must the electric field be at the planes in order for us to know that this is the charge configuration that makes that happen. And some of the things that we might remember are that on the planes we have that the potential must be constant. So because they're conducting, all of the charge will distribute in such a way that the potential is constant and not changing along this plane in both directions. And the electric field, so E, must be perpendicular to each plane, at the plane, so at the surface of the plane. So what that means is that the electric field at every point along here, exactly at the surface of the plane, will be perpendicular. There can be no parallel component. And that's due to some of the conditions we found in chapter 2, the boundary conditions on the surface of a conducting plane. So at every point along here, the electric field must be perpendicular. And the only way that happens is when we have this extra negative Q in the bottom left-hand corner in order to negate the effects that these positive charges have on each other. So you can see right at this point in between, of course, the plane will be moving from, the field will be moving in this vertical direction, and here will be horizontal. But of course, the charges in the top corners here will have an effect on each other, and the only way that in this corner here the conditions will be met is if we put that negative charge in this corner here symmetrically. And that's what my notes say here. So I think here I've drawn the arrows in the wrong direction, because of course the negative charge will see the electric field moving towards it. But this is just to signify the fact that it's perpendicular to that plane, and there are no parallel electric field components along the surface of this conducting plane. So again, for part A and part B, we want to draw the charge configuration through the method of images, which just suggests that we reflect our charge across each conducting plane, and we have to include the charge in order to complete the negative, positive, negative, positive. That's how I kind of remember it. We can never have a negative, positive, positive. It always has to be an oscillating positive and negative configuration, and we put in the required amount based off of the angle that this conducting plane has formed, which is kind of described in your 3.2 notes. And the physical conditions that must be satisfied for this to be the configuration are that the potential must be constant along each plane, and that the electric field must be perpendicular and have no parallel component at every point along the plane as well. For part C and D of question 1, we're given that at some point r, capital R vector, a distance in this connecting plane, so it's a distance r away that's much, much greater than the distance from the connecting plane to the negative charge Q, and the magnitude of r is also much, much less than the infinite size of the conductors. So we can assume that this point is far enough away from the charge negative Q that D is small in comparison, but it's not far enough away that it conflicts with our boundary condition of the plane going to infinity. So that's the conditions on the point R, and the potential at this point R is just some general VR. Now what it wants us to do is it wants us to find the potential at, so this is part C, doesn't erase very well, at part C. It wants us to find what is the potential at the point 2r. So we're not at r, we're at 2r, a distance 2r away. Now we know that due to the multipole expansion that our potential V is going to be proportional to the sum of the expansion of our quadrupole moment, our dipole moment, our monopole moments, and et cetera, our octupole, and if we consider all the terms. Here though, however, we see that we don't just have one charge. Because of the method of images, we can assume that the potential that we see in this upper region from the negative charge and the conducting planes is the same potential that we would see as if this conducting plane was not here, and instead we had these 4 charges. That's the method of images, and that's why we use it. So we see that there is not a monopole moment because we have more than one charge, so that goes away. And we see that the dipole moment here that we receive from these 2 charges will be P1, we can call it, and it's going to be negative Q dy. You can see that, negative Q times dy hat. So it points from the negative charge to the positive charge in the negative dy hat direction, magnitude of Q. And we have the other dipole moment due to these 2 charges over here as P2 is equal to positive Q times dy hat. So again, magnitude of Q, and it's in the positive dy hat direction. So what we see is that for the dipole moments, we have 1 dipole moment and 2 dipole moments. So the total dipole moment is the sum of the 2, which is just equal to 0, because we have equal and opposite magnitudes due to the combination of these 2 dipoles that we see on the left and right. Now what that means is that the dipole moment is also equal to 0. So we have no monopole moment and no dipole moment. So the next most important term in the expansion is the quadrupole moment, which indeed we see negative, positive, negative, positive, which is kind of indicative of the shape of a quadrupole moment. So we can determine that the potential would be kind of similar to what we would see from the multipole expansion of a quadrupole moment at the point 2r, and we know that the quadrupole falls off as 1 over r cubed. That's just how we define the quadrupole in the multipole expansion. So if we're looking at the point 2r, essentially like we're saying little r is equal to 2. So our potential that we see at point r will have fallen off by an extra factor of 1 over r cubed, which is 1 over 2 cubed. So we see that our potential is VR, which is at the point r, divided by 2 cubed, which is equal to VR over 8. So the potential V at the point 2r is equal to VR, which is the potential at the point r, divided by 8. And this 8 comes from the fact that we're at the value 2r, and due to the multiple expansion, we're going to fall off as 1 over r cubed of the quadrupole moment that we see here. No dipoles, no monopoles, because the dipoles cancel, one positive, one negative, and the monopoles, none of them exist. Part D we can also do very quickly here, just squeeze it in, because we're looking for the potential at negative r. But if we're looking at negative r, that means we're looking in this direction, negative r, so we're inside of the conducting plane, so we're on this side of the mirrors, of the images, which means that we're in the region where we define the potential to be equal to 0, because inside of the conducting planes, inside of a conductor, the potential is equal to 0. So just due to the fact that we have by definition distinguished that the potential inside of a conductor or inside of these conducting planes is equal to 0, if we're looking at the potential for the point negative r, that's just inside the planes, we can right away say that V of negative r is equal to 0. So part C, we say that V at 2r is the potential given at point r, V of r over 8. We don't actually know what V of r is. Doesn't matter, he just gives it to us in the problem as some sort of constant potential that we know at the point r, and it falls off as 1 over 8 due to the multipole expansion at the point 2r. Inside the conductor, Vr is just equal to 0.